Hello everyone and welcome to another video. In today's video, we are going to be exploring a few rules for determining the derivatives of polynomial functions. And so just like we have different rules for working with algebraic expressions, for working with exponents or logarithms or even trig, we also have rules that simplify the tedious process of using limits for differentiation. So if you have watched my previous video, we know that we used first principles along with limits to find the derivatives of functions, and that was a fairly long process. Well, not to panic, we do have some rules that we can use that are going to streamline this process. So let's start by recalling an important concept here. The concept that the derivative of a function is the slope of the tangent to any point on the curve as a function of its x value. So basically, the derivative, again, in and of itself, is a function where each y value is the slope of the tangent point at that x value, at its respective x value, okay? And so again, previously, we have seen how to compute the derivative using first principles. So that was by using limits. We were taking the limit as h approaches 0 of f of x plus h minus f of x over h. And again, this formula comes from the slope formula, right? Where we have the change in y over the change in x. So again, if we have a function, right, and we have 2 points, these points are going to have coordinates x1, y1, and x2, y2. But again, the goal of this video is to show you a different way for finding some of these derivatives, specifically when it comes to polynomial functions, that are not going to require us to use the formal definition of the derivative. They are not going to require us to use first principles. So let's start by looking at the first rule, which is the constant function rule. Okay, so given a constant function, f of x is equal to k, what is the slope? So for example, here we can have f of x is equal to k. Some examples would be y is equal to 3, or y is equal to 1/2, so on and so forth. Basically, this means, visually, that we would just simply have a horizontal line as our function, okay? And so the derivative of a constant function is 0, okay? So this gives us our first rule, because the slope is going to be 0, right? And remember that the derivative is the same as the slope at a specific point, right? And so here, for all of these points, the slope is always going to be 0, right? There is no change in y as x changes. And so this is going to give us our first rule. If we have a constant function, if we have f of x is equal to k, where again k is a constant, then f prime of x, or the derivative of that function, is equal to 0. Again, a quick example here. If we have that f of x is equal to 5, well, then the derivative of 5 is just simply equal to 0. Our second rule for today is the power rule. And we are going to derive this rule step by step. We are going to start by exploring the function x squared, the quadratic function. So given this quadratic function, we want to find f prime of x. So here, let's go back to the formal definition, to first principles. It is going to be a little bit of work, but we are going to see a pattern emerge. So again, with first principles, we would have the limit as h approaches 0 of x plus h squared minus x squared over h. And now, of course, we expand and simplify. So we're going to have x squared plus 2xh plus h squared over h minus x squared. The positive x squared with a negative x squared cancel out. And this is going to give us the limit as h approaches 0 of 2xh plus h squared over h, which we are going to factor in the numerator. So we factor out the h like we have done previously. And we are going to have 2x plus h over h. Now the h's cancel out. And we are going to be left with the limit as h approaches 0 of 2x plus h. So now we directly evaluate the limit, and our derivative is going to be equal to 2x. Perfect. Now, what if instead we had the cubic function? What if instead we had x to the power of 3? Let's again try and find this derivative. Once again, we are going to use first principles. That is the only technique that we have as of right now, right? So again, same process. A little tedious, but we are getting used to using it. We have the limit as h approaches 0 of x plus h to the power of 3 minus x to the power of 3 over h. We expand and simplify. So we're going to have x to the power of 3 plus 3x squared h plus 3x h squared plus h cubed minus x cubed all over h. And now here, of course, we see that we can cancel out the positive x cubed with the negative x cubed. And once again, we factor out an h term from the numerator because all of the remaining terms contain an h factor, right? So factoring it out, we are going to have h times 3x squared plus 3xh plus h squared all over h. We cancel out the h in the numerator with the h in the denominator, and we are going to be left with the limit as h approaches 0 of 3x squared plus 3xh plus h squared. And now I am able to directly evaluate the limit, and I'm going to have 3x squared plus 3x times 0 plus 0 squared, which is, of course, just simply equal to 3x squared. And that is going to be the final derivative for x to the power of 3. Okay? So again, keeping tabs on what we have so far, the derivative for x squared is 2x. The derivative for x to the power of 3 is 3x to the power of 2. Okay, maybe you're starting to see a pattern. I think maybe we need to do another function just to be sure of what we are observing. So now let's go 1 degree higher and let's try and find the derivative of x to the power of 4. So again, using first principles, the derivative is going to be equal to the limit as h approaches 0 of x plus h to the power of 4 minus x to the power of 4 over h. We expand. Limit as h approaches 0 of x to the power of 4 plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the power of 4 minus x to the power of 4. All right, fully expanded, and now we simplify by canceling out the positive x to the power of 4 with the negative x to the power of 4. And now this is going to leave us with an expression that has a factor of h for every single term in the numerator. So we are going to again factor out that h. As you can see, it's always the same process for each polynomial here, right? So h times 4x cubed plus 6x squared h plus 4x h squared plus h cubed, and this is going to cancel out with the h in the denominator. There we go. And we are going to be left with the limit as h approaches 0 of 4x cubed plus 6x squared h plus 4x h squared plus h cubed. And now I'm going to directly evaluate the limit so that I have 4x cubed plus 6x squared times 0 plus 4x times 0 plus 0 cubed, which of course just simplifies to 4x cubed. And that is my final derivative. The derivative of x to the power of 4 is equal to 4x to the power of 3. So let's generalize this pattern that we are seeing. If we have x to the power of n, where again x is a real number, then the derivative, so means that x is a real number, so and again n is also a real number, n can be negative, n can be positive, the exponent, it does not matter, all right, n is also a real number, then the derivative of that function is going to be given by this rule, where we have n times x to the power of n minus 1. So what is happening here? We are going to bring down the exponent and we are going to multiply it by x to the power of n minus 1. So we bring down the exponent and we multiply it instead, and the original exponent we are going to subtract 1 from it. Okay, so let's see a few examples here. All right, for example, continuing the pattern, if we have x to the power of 5, then the derivative is going to be equal to 5, bringing down the exponent, multiplying it by x, and now I'm going to subtract 1 from the original exponent. The original exponent was 5, subtracting 1, the new exponent is going to be 4. Okay? Like I said, the exponent does not necessarily have to be positive, right? So let's try it with a negative number. Let's see, f of x is equal to x to the power of negative 3. Again here, the derivative is going to be equal. Remember that x to the power of negative 3, this is the same as having 1 over x to the power of 3. So remember that you are able to rewrite functions as you see fit, as it makes it easier, okay? Because if we have a rational function here, we can rewrite it using exponents, and it's going to make it easier to take the derivative, okay? Because then the derivative, again, we are just going to use our rule. Negative 3 is going to come down. I'm going to multiply it by x, and I'm going to subtract 1 from the original exponent. Negative 3 minus 1, it is just simply going to be negative 4. Okay? So instead, I'm going to have negative 3 times x to the power of negative 4. And then, of course, I could rewrite it as a rational function again. Okay. And like I said, n is a real number, so it does not have to be an integer. It does not have to be a positive whole number or a negative whole number. It can be a fraction. So for example, if f of x is equal to x to the power of 1/2, which again is the same as having the square root of x. Remember that we can represent square roots using exponents, right? Or really any roots using exponents. Then its derivative can also be found using the power rule. So again, we are going to bring the exponent down as a constant that we are multiplying by x, and now we are going to subtract 1 from 1/2, right? So here we are going to have 1/2 minus 1, which is the same as having negative 1/2, right? If I grab a common denominator, this is the same as having 1/2 minus 2/2, which is equal to negative 1/2. So I'm going to have 1/2 times x to the power of negative 1/2, which again I can rewrite as a square root function, okay? Which is going to be equal to 1/2 square root of x. And that is the power rule. The next rule that we are going to look at today is the constant multiple rule. And this rule states that if f of x is equal to k times g of x, where here again k is a constant, just a real number, then that tells us that the derivative is going to be equal to k times g prime of x. Okay? Or basically just, instead of g, let me just use the same notation, k times f prime of x. So we are just going to basically factor out that constant. That constant is going to stay in place. We take the derivative and then we just multiply it through at the end. All right, we have an example here. Let's say that we have the function f of x is equal to 3x squared. Okay, so then f prime of x, I am just going to leave that 3 there, that constant, untouched, and I am going to take the derivative of my function here of 3x squared, okay? Or here in this case, pardon me, the original notation was correct, g prime of x. So here, g of x, right, is given by x squared. So I'm just going to take the derivative of x squared and the derivative of x squared is equal to 2x, like we have seen previously, right? So now all I have to do is to multiply these two together to get 6x. So the final derivative is equal to 6x. And this is something that we have seen previously with the limit, right? Just as constants were unaffected by a limit, so are derivatives. So we can just factor out that constant basically, and then we multiply it through in the end. Okay? we treat it as if it's not there, we take the derivative, and then in the end, we account for it. So that is a constant multiple rule. The final rule that we are going to be looking at today is the sum/difference rule. And this rule states that if we have two functions, p of x and q of x, and both of these functions are differentiable, and f of x is equal to p of x plus or minus q of x, then the derivative of f of x is just simply going to be given by the sum or difference of those two functions. Okay, we are going to have that f prime of x is equal to p prime of x plus or minus q prime of x, depending on whether we are adding or subtracting the functions. So let's take a look at an example here. Okay, let's say that f of x is equal to 2x squared plus 3x to the power of 4, right? So in this case, we have p of x, okay? And we also have q of x. Well then, we take each derivative individually. So here we are going to have 2 times x squared, that's going to be equal to 2 times 2x plus 3 times x to the power of 4. The derivative of x to the power of 4 is 4x to the power of 3. We multiply it through, and we are going to have 4x plus 12x to the power of 3. Where, of course, 4x is the derivative of 2x squared, and 12x cubed is the derivative of 3x to the power of 4. Okay, so again, we are just going to take the derivatives individually, and then, of course, we are adding them in the end. In this case, we have two terms with different degrees, so we cannot add them beyond this step. But if they were the same degree, then we would be able to add them and simplify further. Okay, so let's put all of these rules together and practice with a few examples here. So differentiate the following, starting with part A. F of x is equal to 3x to the power of 4. So here again, we need the constant rule and the power rule, right? We are going to have f prime of x is equal to 3. Now I'm going to leave 3 alone because it's the constant, right? And I'm going to take the derivative of x to the power of 4. That's my g of x, right? That's the function that I want to take the derivative of. So here again, using the power rule, I am going to bring that constant down, that exponent down as a constant, x, and then I subtract 1 from the original exponent. So I'm going to have 4 minus 1. Simplifying, I'll have 3 times 4x to the power of 3, and multiplying through, I'm going to have 12x to the power of 3. And that is the final derivative. Let's see a similar example, but now involving some negative signs here. Part B, if we have f of x is equal to negative 7 times x squared, well then f prime of x is going to be equal, leaving negative 7 alone, I take the derivative of x to the power of 2, which is just simply going to be equal to 2x, and now I can multiply it through, right? Negative 14x. Another example, f of x is equal to 10 times the square root of x. Remember here, we don't have a rule for square roots, but we have a rule for exponents, right? And remember that we can rewrite a square root as an exponent using the exponent of 1/2. So having 10 times the square root of x is equal to having 10 times x to the power of 1/2. So f prime of x is going to be equal to 10, just leaving my constant alone. I am bringing the exponent down as a constant and then subtracting my original exponent by 1. We have seen this one before, right, in a previous example. So here I am going to have 10 times 1/2 x to the power of negative 1/2. And now I multiply through 5 times x to the power of 1/2. Now the function was given to me in the form of a square root. So just for consistency, the answer should also be given using square roots. So 5 over x to the power of 1/2, which is equal to 5 over the square root of x. And that is going to be my final answer for the derivative. Okay. So all of these questions all involved the constant rule and the power rule. Okay. Let's take a look at another function now that's going to require us to also use the sum/difference rules. Okay. So in this case, we have part D, f of x is equal to x to the power of 4 minus 3x to the power of 3 plus 2x minus 7. So really, what we have here is 4 separate functions that we can take the derivative of. Okay, so let's start here with x to the power of 4. So starting with x to the power of 4, we take the derivative. So that's going to be 4x to the power of 3, right? And now we are going to subtract the derivative of 3x to the power of 3. Well, we're going to leave 3 alone. That's going to be our next function. We are going to leave 3 alone. Now we take the derivative of x to the power of 3, which is going to be 3x to the power of 3 minus 1, which is just 2. And then we add the derivative of 2x. So that's going to be 2. And then I take the derivative of x. And x, I can also treat it as a power function, right? Having x is the same as having x to the power of 1. So really what I'm going to do is that I'm going to subtract 1 from the exponent. So I'm going to have x to the power of 1 minus 1. And then I am finally going to subtract the derivative of 7. And remember that that was the first derivative that we talked about, which is the constant rule. If I have a constant function, then the derivative of the constant function is just simply equal to 0. All right, and that is what I am going to do. All right, so again, treating each function or treating the function, the main function, as 4 separate functions that I am taking the derivative of individually. Okay, so now all I have to do is, of course, simplify. So here I'm going to have 4x to the power of 3 minus 3 times 3 is 9, x squared plus 2x to the power of 0. X to the power of 0 is really just equal to 1, right? And then, of course, the minus 0 can just go away. So in the end, I am going to have 4x to the power of 3 minus 9x squared plus 2. And that is the final derivative. One final example here. F of x is equal to 2x plus 1 to the power of 2. Well, what do we do in this case? We have talked about using the power function when we have just x to the power of 2 or x to the power of 3, right? What if we have a whole expression here? Well, we don't really have the rule for these types of functions yet, but what we can do, which will allow us to use the rules that we already have, is that we can expand this function, right? 2x plus 1 squared is equal to 2x plus 1 times 2x plus 1, which is going to be equal to 4x squared plus 4x plus 1. So now here again we have a polynomial with 3 terms. Each term is technically its own function, and I can just take the derivative of each of the terms individually. So f prime of x is going to be equal to the derivative of 4x squared, which is going to be equal to 4 2x, right? Now plus, and I take the derivative of 4x. Again, this is going to be the same as having 4x to the power of 1 minus 1, which is just going to be x to the power of 0 or 1. And then finally, I'm going to take the derivative of 1, which is going to be equal to 0, because it is a constant. Putting it all together, I am going to have 4 times 2x is equal to 8x, plus 4 times x to the power of 0. Again, remembering x to the power of 0 is equal to 1, and the 0 can just go away. The final derivative is going to be equal to 8x plus 4. (8x plus 4). Okay, so hopefully these examples have been helpful to help you see how we can use all of these rules together in order to find the derivatives of different functions. Now let's apply these rules for a more thinking problem, all right? So here, determine f prime of -2 for the function f of x if f of x is equal to 2 over x squared. So here again, we have a rational function, but let's recall that we are able to rewrite rational functions using negative exponents, right? So we are going to rewrite f of x as f of x is equal to 2 times x to the power of -2, okay? And so now we are able to use the power rule in order to take the derivative of this function. Doing so, we end up with 2 times, now I'm going to take the derivative of x to the power of -2, so I bring that exponent down as a constant, multiply by x, and now the original exponent on x, we are going to subtract 1. So let's simplify all of this. We are going to have 2 times -2, x to the power of -3, and so this is going to be equal to -4x to the power of -3. And again, because I was given the original function as a rational function, I am going to rewrite this expression with negative exponents into a rational expression. So -4 over x to the power of 3. And that is my derivative. But now I'm not just looking for the derivative, I am looking for the derivative at x is equal to -2. So now I know that f prime of x is equal to -4 over x to the power of 3. So to find f prime at 2, all I have to do is plug in 2 for x. So here, or -2, pardon me, not +2. So all I'm going to do, -4 over -8. The negatives cancel out. I'm going to simplify 4 over 8 as 1 over 2. And that is going to be my final answer. What is the significance of this answer though? Why do I want to plug in a specific value for the derivative? Well, because this gives me the slope of the tangent for the original function at the point x is equal to -2, right? So the significance is that this is the slope of the tangent to f of x at x is equal to -2. So basically, once I have the general derivative, the general function for the derivative, I can plug in any value of x, and that is going to give me the slope at any given point. Okay? So again, remember that the derivative is a function in of itself, and it is a function that gives you the slope of the tangent at any given point. Okay? So I hope that this video was helpful, and I will see you in the next one. Bye!